Yes, a warm welcome to all you friends of Restful Sleep and everyone interested in sleep research and sleep medicine. Now that I've finished my caffeinated beverage, we can continue with our next episode of Sleep Lab with Netzer and Popovich.
And as we promised in the last episode, today we'll show you the curves that are generated during a sleep lab recording, and we'll also discuss the associated sensors and electrodes.
But unfortunately, as is so often the case in life, before we can get right into it, we have to talk a little about physics, because ultimately it's all about physics. What happens in our brain is nothing other than current flowing from the negative to the positive pole and then back again, alternating current. What we record is simply flowing current. And we call the whole thing an electroencephalogram, where the word cephalo stands for brain, and electrogram means we're recording electricity. Let's take a quick look at the image here. You see two nerve cells, and these two nerve cells with their so-called dendrites, those are the branches. You can imagine them as cables, like small thin wires. This is where the current flows from one to the other. We can also just simply draw this out. Ultimately, it's quite simple. We basically just have a current flowing from the negative to the positive pole and back again. And then we have a wonderful, very simple current spike. In principle, you all know this from many movies. For instance, in earthquake disaster films, when the seismograph needle goes back and forth, or in spy thrillers when a lie detector is used. In that case, you're also measuring the electrical current that flows in the brain using electrodes. So how does the current flow? I've already mentioned it. On the one hand, we have a direct current, but in the brain, it's no different than our wall socket. We have alternating current. Now, the alternating current from our socket is 50 hertz, meaning the current flows from plus to minus 50 times per second. And in the electroencephalogram, or rather in our brain, the current can flow back and forth faster or slower. Large spikes, I'll just quickly draw this for you on a graph, have a larger amount of current and a higher voltage. And then when it gets faster, the spikes are smaller, but the frequency is higher, just as I said, like with alternating current. Although they are actually current spikes that move up and down on a horizontal line running from left to right over time, we refer to them as waves and patterns. Here we look at the frequency of these spikes and their deflection height, which is called the amplitude. Based on the characteristics of these waves, we assign a sleep stage to each 30-second epoch, such as light or deep sleep, as well as REM sleep. These can be displayed in a graph over the entire night, which we then refer to as the sleep architecture.
In the graph shown here, the different sleep phases are displayed. There is the awake state, light sleep, sleep stages 1 and 2 with a fast rhythm in the EEG, deep sleep, sleep stage 3 with a very slow rhythm of the waves in the EEG, and REM sleep or rapid eye movement sleep, also known as dream sleep with eye movements. The graph shows the percentage shares of the individual sleep phases in relation to the total sleep duration.
And for that, we'll now switch back to the sleep lab in Bolzano and take a look at this in reality. So, we're now back in the sleep lab in Bolzano, and Heike and I will now evaluate the electrophysiological channels and create a sleep profile for the patient. Heike, please describe in detail to us which channels we need to evaluate the sleep and also at what intervals you assess it.
Okay. We have our EEG channels here. These are the ones we wired to the head earlier. We have our EOG here, so we can monitor and see the eye movements, and the chin EMG to observe what the body tension is like. Here we have the awake stage. This means we have beta waves of 13 hertz or more. We evaluate this in 30-second intervals as required by the AASM, and now we'll see what the patient is doing.
So if I understand you correctly, you always take a 30-second period, and that 30-second period is defined by you based on the waves to determine which sleep stage is present in that 30-second period. Is that right?
That's exactly right, and all according to the rules of the ASM. That's precisely prescribed. Here, for example, we see the awake state. You can see the patient's eye movements. They're looking around the room. The EMG is still relatively high. We'll see in a moment what it looks like when it's very low.
So by high, you mean there are still strong muscle movements that you've recorded from the chin, right? Exactly.
And here we see beta waves, which are faster than 13 hertz. Hertz just means the oscillation per second. And now I'm pressing awake, 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 and look.
But just briefly, actually, because we had this explained during our studies. So hertz means it's alternating current, yes, like from a power outlet, just not with 50 hertz like our outlets, but here, when awake, and that's the normal state in the brain when we're awake, 13 hertz.
Exactly, precisely. And here the patient still had their eyes open. Now they would close their eyes. We're here in an alpha rhythm of 8 to 13 hertz. The eyes are slowly starting to roll. That's a sign of great drowsiness. And when I see that here in my recording, then I know it's possible that the patient is about to fall asleep. But he doesn't. You never know what the next page will bring. Instead, he looks around again. And so, but if we go back one page now, we can already see the first theta waves.
Can you go back briefly to that one spot where the patient briefly woke up while falling asleep?
Mm-hmm.
That's the point. Patients often describe twitching with their legs. So there's something else happening in the brain between being awake and asleep, right?
Yes, that's exactly right. These sleep twitches, we've all experienced them before. When you're dozing off and you get the feeling that you're falling out of bed, that's when discharges happen again. And something like that could have happened here, of course. Or he heard a noise, something happened. In any case, he woke up really nicely again here, only to then slowly doze off. You can really see the frequency slowing down to theta, 4 to 8 hertz, and the eyes are rolling. Those are slow eye, sorry.
Yes, we had beta with 13 hertz.
Right. When closing the eyes, we had alpha
with about 8 hertz. And now we have theta with 4 hertz.
Exactly. And those are slow eye movements, which are slower than 500 milliseconds. And here we're looking now, do we already have 50% of this epoch? That's what we call these 30 seconds that we're seeing right now. Is it more than 50%? Sometimes you can't really tell. We have 5 seconds here, 3 seconds. So I would say it's still an awake state. And here, slowly, he's actually falling asleep. We have a beautiful theta frequency here and can now assign a 1. What we see here is the automatic analysis of the device. It always does a pre-analysis, but if you're a pro, then of course you
would correct it now.
Exactly correct it.
And that's perhaps also the point why it's so important that we humans are still here in the sleep lab, because the robot can't do it alone yet.
No. It has very clear algorithms, but here he has now fallen asleep. But we see a frequency acceleration here back to a beta. And now we can mark what's called an arousal here. An arousal is a waking reaction, a frequency acceleration of at least 3 seconds caused by, in this case we don't know yet, but the computer can recognize the connections between leg movements and arousal reactions, or respiratory events and arousal reactions, and it does that very well. If it doesn't recognize anything, it just marks it as a spontaneous arousal. And now let's see, we still have over 50% of this nice theta rhythm and continue to assign a 1. Here, he's falling asleep again, beautiful theta. And here, do you see that? There's another arousal. That means he's not really trying to do much of anything.
So, it's back and forth between completely asleep and awake.
Right.
But I don't think patients notice that anymore, or rather, people who are sleeping, I don't think they notice these small arousals, do they?
No, you actually don't remember the many small arousals, only if you stay awake for a certain amount of time. Otherwise, you would also remember every time you turn over or pull the blanket back up. When the night is over, you can't remember it anymore. But he's trying, isn't he? He has his rolling eye movements again, his slow eye movements, but he's not succeeding. So now we'll go through it page by page. And of course, as we sit here, we're hoping, hey, I hope you get some good sleep. And the computer has marked an arousal here, so let's remove that. And now I'm hoping for a 2 right away. And here, if I may scroll forward a bit, in the second half of the epoch, we see this strange thing. It goes up into the negative and down. And that is a so-called K complex. This K comes from knocking, because it was discovered that you can trigger these, they're called grapho elements, by knocking, which is why it was named the K complex. And that is now a grapho element.
To knocking.
Exactly, knocking. And this is now a grapho element that shows us he is now entering sleep stage 2. However, it's hidden way back here in the second half of the epoch. So for now, we'll give it a 1 again, and now he's in stable sleep. We still see our theta frequency, but now increasingly with these grapho elements, the K complexes also include spindles. Spindles are small interspersions of, again, a very fast frequency, an alpha frequency, which we might also see in this patient now. In any case, these are signs of stable sleep, of sleep stage N2.
That would be something to do with simple sleep arithmetic.
Exactly. We distinguish between non-REM and REM sleep, light sleep and deep sleep, and we are now in a stable light sleep state in N2. And now we see the computer has added another arousal here, but that's what we're here for. What we are actually waiting for now are so-called delta waves. Delta waves have a frequency of 0.5 to 4 Hertz. They have a maximum height of 75 microvolts, that's what it's called. And we have guidelines for that, so you can see it at a glance. That's what we're actually waiting for. If 20% of the epoch shows these high delta waves, then we may, as 3 values. Now we have it here. Beautiful delta waves, also called slow wave waves, when they are between 0.5 and 2 Hertz. And these K complexes, if they increase the target, may even be included, as in this case. There is a K complex there now, but this is a beautiful stage 3 sleep. But
as a professional in your field, you might also be using the EOG, which stands for electrooculogram, and the EMG or electromyogram, right? Both in deep sleep.
Very well observed. According to the ASM, eye movements are not observed during deep sleep. That's partially true. Of course, these are not specific eye movements, neither during REM sleep. However, since deep sleep is depicted frontally, waves that practically adapt to these high delta waves can also be seen in the EOG. These are actually artifacts. These are not typical eye movements, but if there are high waves in the eye in the EOG, then they indicate that it is deep sleep. We're now in a deep sleep. It's wonderful. Now we can really step on the gas a little bit. These are the phases we as evaluators prefer because you can really step on the gas. And deep sleep is usually a longer phase. But now we've seen here the first rough one is already here. But we can still sleep soundly now. But now he's awake. Something woke him up.
Because it's normal for there to be a short waking phase after such a deep sleep phase.
Exactly. We are back in sleep stage 1. We're seeing a small wake-up call here again. We're waiting for our graph elements again. Here's a K complex. And now we can, that's not right, 2. 2. Here in the occipital lead, which clearly shows the difference between being awake and asleep. I don't see any acceleration, so I'll remove the marker. We have So what I'm actually waiting for now in the sleep cycle, what you'd expect is light sleep, deep sleep, and then comes dream sleep. And that's what I'm waiting for now. Let's see if it happens. The computer sometimes is a bit overmotivated sometimes, but that's what we're here for. Yes, now slow delta waves are coming in again. They don't quite meet the criteria yet. If we now just...
Yes, what was that?
Now she startled me. So you can recognize REM sleep firstly by the mixed frequency that appears here. It's a kind of theta frequency, but it can also be faster and slower at times. It's called LAMF, low amplitude mixed frequency. But a very clear characteristic are the opposing eye movements, which are also the REMs, these rapid eye movements. They are faster than 500 milliseconds. We just had the slow eye movements with less than 500 milliseconds. And then the chin. REM sleep, that's the most relaxed state during all the sleep stages.
So for us, the EMG is also always very important because it's practically at zero, a flat line.
Right, at zero, yes, definitely at the lowest level of the entire recording. But we don't quite have that here yet. I'll speed things up a bit. You're really allowed to do that in this case. So I always look here, especially in the O2, to see if there's a frequency acceleration, and then I assess whether it's an arousal or not. Yes, here's a small frequency acceleration. That's an arousal. Later, if we were to evaluate the respiration, we would also see if it's actually related to a breathing problem or if there's a leg movement behind it. Now you've seen the frequency is starting to get mixed here. I'll go back one or two so we can observe it nicely. Here you can still see a grapho element like a spindle. It's a bit long for a spindle, but here we still have a K complex. That's definitely still a 2. Here's another K complex. There's a K complex 2. But here you can already notice this mixed frequency, yes. And now I'm actually expecting the eye movements to start any moment because the EMG is at its lowest level. I'll mark it as N2 again. Here you can see the first eye movements, even if they're not yet typically sharp, conjugate and fast. But also on the screens before, when the EMG is very low and no more grapho elements are visible, you can already score it as REM. And here's the proof. Yes, these are the rapid eye movements in combination with the lowest EMG of the entire recording.
You can also see nicely that the eye movements are in opposite directions.
Exactly.
So one eye goes left and one eye goes right. There are people who can do that. Consciously, I can't.
Me neither. No. If you're thinking that's a K complex, no, it's just a vertex sharp wave or a slower wave, and now we're going into REM. Now comes a special case. The computer has marked an arousal here, but it's not one at all. Because in REM, arousals can actually only be scored if there's an EMG increase of at least 1 second. That means there's no arousal here at all, but rather it's more proof of this mixed frequency that we see in REM. No, that's nothing to worry about here. Here are a few spindles. So at least we have an example of a nice spindle. Another grapho element for sleep stage 2 is a K complex.
How long has the patient been asleep now? I think
we're at a good hour now, aren't we? Yes, right? And so 200 epochs of 30 seconds each.
So that would be the normal progression as we'd expect. So first you have, yes, wake, sleep, then light sleep in a certain sequence. Then the first deep sleep phase comes relatively quickly because we also need to recover. And then when that's over, after a short light sleep phase, comes the first REM or dream sleep phase.
And we're interrupting our dream sleep now, actually, right? You could see it coming on the previous screen. Here comes an arousal reaction, and here you can actually see this increase. You can see it really, really nicely, this low amplitude EMG, and then an increase here. That means there was a wake-up reaction here, a so-called arousal. And that actually ends our REM when rolling eye movements appear, which they do.
Which is normal. So we switch back and forth relatively quickly at the beginning. The deep sleep phase is a bit longer, as you showed. You said you could speed through it. Can you go to the end of the night to see if we can see these longer REM sleep phases again? That's perhaps something people aren't so aware of, that what they dream at the beginning of the night, they're less likely to remember, but then the REM gets stronger and stronger. Can we take a look?
So can you go to the end of the night? Yes.
To see if we have strong REM there?
Yes. Of course, this isn't an arousal either, because the EMG is again at its lowest level. One of the electrodes has come off here, but that doesn't matter at all, because an experienced scorer can still evaluate it perfectly, even with a faulty electrode. There are even some scorers who claim they can evaluate an entire polysomnography based only on the EOG and EMG. I don't know if that's entirely accurate, but it's said to be possible. Here too, we have no increase in the EMG, which means we're staying nicely in REM. And especially for people who think on the weekend, now I'll sleep in and then wake up feeling completely exhausted. People who normally get up at 6 but then get up at 9 on the weekend, there's a reason for that. Towards the end of the night, you have more REM sleep, and that's not restful. That's just how it is, right? Deep sleep is what's restful, and N2 is also restorative. But this REM sleep, if you have more of it during those morning hours when you would normally already be up, it wears you out. I'm sure everyone knows that feeling. You should always, at the same time,
get up. But that's precisely the sleep where people then remember that they're dreaming, right? Those are the dreams that stick with you, so to speak. Sometimes even more nightmares during this time. And maybe we should also tell the viewers something about when this REM sleep occurs right at the beginning of the night instead of deep sleep. That's not entirely normal.
no.
Instead, it actually provides us with a significant clue about a particular disorder, and that disorder is known as narcolepsy. Because certain specific things in the brain are not functioning properly, it results in the patient experiencing REM sleep right at the very beginning of the night.
Exactly. I often work in a neurological sleep lab. We have many narcoleptics, and you'll see REM sleep just 2 minutes after they fall asleep, so a very short REM latency. And that's a clear sign of narcolepsy. When the daytime studies are done, they lie down, fall asleep instantly, and start dreaming instantly. And that's unusual, which is why it's pathological, narcolepsy. And they have an incredible tendency to fall asleep. So we've reached the end of the night here.
But now let's put together a sleep profile from everything you've evaluated.
We now have the hypnogram here. That means in total, when I'm done, I've evaluated 935 pages, all individually. And from that, this hypnogram is created, which shows how the individual sleep stages are composed. This thick band is then REM sleep. You can see it clearly here with the eye movement, right? This thick part here. And we have the deep sleep with our delta waves, right? And in between, we have our light sleep, and very rarely in this patient, our waking phases.
Yes, although you are allowed to be awake for a bit. That's often overestimated by the patients, but I would say, or we can agree, that this is now an almost completely picture-perfect sleep profile, wouldn't you?
That's the sleep profile that every scorer urgently wishes for.
Yes, dear viewers, that was, so to speak, the ideal evaluation of the night's neurophysiological channels. In the next episode, we'll then deal with the respiratory channels, and until then, this time not from the studio, but here from Bozen. Goodbye, everyone, and sweet dreams.
Bye.